Today we're diving into the fascinating world of semiconductors, focusing on a crucial concept, the band gap. Whether you're a student, an engineer, or just curious about how modern electronics work, understanding the band gap is essential. This invisible energy barrier plays a key role in determining how materials conduct electricity. Over the next several scenes, we'll break down what the band gap is, why it matters, and how it shapes the technology we use every day. Let's start by exploring the basics of energy bands in solids and set the stage for a deeper understanding of semiconductors. Solid materials, atoms are packed closely together and their electrons interact. Instead of having distinct energy levels like isolated atoms, these interactions cause the energy levels to spread out, forming what we call energy bands. The two most important bands are the valence band, where electrons are usually found, and the conduction band, where electrons can move freely and conduct electricity. The arrangement and spacing of these bands are fundamental to understanding how materials behave as conductors, insulators, or semiconductors. Band gap is the energy difference between the top of the valence band and the bottom of the conduction band. Think of it as a forbidden zone where no electron states exist. For an electron to jump from the valence band to the conduction band, it must gain enough energy to cross this gap. The size of the band gap determines whether a material is a conductor, semiconductor, or insulator. In semiconductors, the band gap is just right, not too large, not too small, allowing for controlled conductivity. Really grasp the importance of the band gap, let's compare conductors and insulators. In conductors like metals, the valence and conduction bands overlap, so electrons can move freely, making these materials excellent at conducting electricity. In insulators, the band gap is very large, so electrons can't easily jump to the conduction band, resulting in poor electrical conductivity. Semiconductors fall right in between, with a moderate band gap that allows for controlled electron movement under certain conditions. Semiconductors such as silicon and germanium have a band gap that's small enough for electrons to cross when given a little extra energy, like heat or light. This unique property makes semiconductors incredibly useful in electronic devices. By controlling the flow of electrons, we can create switches, amplifiers, and other essential components found in computers, smartphones, and solar cells. The band gap is what makes all this possible, acting as a gatekeeper for electrical conductivity. Let's talk about intrinsic semiconductors. These are pure materials like pure silicon without any added impurities. In their natural state, only a small number of electrons have enough energy to jump the band gap and reach the conduction band. This means intrinsic semiconductors have limited conductivity at room temperature. However, their properties can be dramatically changed by introducing impurities, a process known as doping, which we'll discuss in upcoming scene. Extrinsic semiconductors are created by adding small amounts of other elements, called dopants, to a pure semiconductor. This process introduces extra electrons or holes, making it much easier for electrons to cross the band gap. Depending on the type of dopant, we get either N-type or P-type semiconductors, each with unique electrical properties. Doping is a powerful tool that allows engineers to fine-tune the conductivity of semiconductor materials for specific application. Type semiconductors are made by adding elements with more electrons than the host material. For example, adding phosphorus to silicon introduces extra electrons which can easily move to the conduction band. These free electrons increase the material's conductivity. The band gap remains the same, but the number of charge carriers increases, making N-type semiconductors essential for building electronic circuits. P-type semiconductors are created by adding elements with fewer electrons, such as boron, to silicon. This creates holes places where an electron is missing. These holes act as positive charge carriers and can move through the material, allowing current to flow. Like N-type, the band gap doesn't change, but the way electricity is conducted does. P-type and N-type semiconductors are often combined to create devices like diodes and transistors. Temperature has a significant effect on the band gap and the behavior of semiconductors. As temperature increases, more electrons gain enough energy to jump across the band gap, increasing conductivity. This is why semiconductors become better conductors at higher temperatures. However, too much heat can also cause problems, so managing temperature is crucial in electronic device design. Not all band gaps are created equal. In some materials, the band gap is direct, meaning electrons can move directly from the valence to the conduction band by absorbing or emitting a photon. In others, the band gap is indirect, requiring a change in momentum as well as energy. This distinction is important for applications like LEDs and lasers, where direct band gap materials are preferred for efficient light emission. Silicon is the most widely used semiconductor material, and it has an indirect band gap. This means that while it's excellent for building transistors and integrated circuits, it's less efficient for light-emitting applications. That's why materials like gallium arsenide with a direct band gap are used in LEDs and laser diodes. Understanding the type of band gap helps engineers choose the right material for each application. Gallium arsenide is a semiconductor with a direct band gap, making it highly efficient for emitting light. This property is why it's commonly used in optoelectronic devices like LEDs, laser diodes, and solar cells. The direct band gap allows electrons to recombine with holes and release energy as photons, resulting in bright, efficient light emission. This makes gallium arsenide a key material in modern photonics. Band gap engineering is the process of modifying the band gap of a material to suit specific applications. By combining different semiconductor materials or adjusting their composition, engineers can create custom band gaps. This technique is essential for designing advanced devices like multi-junction solar cells, high-speed transistors, and quantum dots. Band gap engineering opens up a world of possibilities in electronics and photonics. Quantum dots are tiny semiconductor particles with unique optical properties. Their band gap can be precisely controlled by changing their size. Smaller quantum dots have larger band gaps and emit light at shorter wavelengths, while larger dots have smaller band gaps and emit at longer wavelengths. This tunability makes quantum dots valuable in displays, medical imaging, and solar cells, where specific light emission or absorption is needed. Solar cells or photovoltaics rely on the band gap of semiconductor materials to convert sunlight into electricity. When photons with enough energy hit the semiconductor, they excite electrons across the band gap, generating a flow of current. The efficiency of a solar cell depends on how well the band gap matches the energy of incoming sunlight. That's why band gap engineering is so important in solar technology. Light-emitting diodes or LEDs are another technology that relies on the band gap. When electrons recombine with holes in a direct band gap material, they release energy as light. By choosing materials with different band gaps, engineers can create LEDs that emit different colors. This is how we get everything from red to blue LEDs, lighting up our homes, screens, and even traffic signals. Transistors are the building blocks of modern electronics, and their operation depends on the band gap of semiconductor materials. By controlling the flow of electrons across the band gap, transistors can act as switches or amplifiers. This ability to precisely control electrical signals is what makes computers, smartphones, and countless other devices possible. The band gap is truly at the heart of digital technology. Diodes are simple semiconductor devices that allow current to flow in one direction only. They're made by joining p-type and n-type materials, creating a junction where the band gap plays a crucial role. When voltage is applied, electrons cross the band gap at the junction, allowing current to flow. Diodes are essential for rectifying currents, protecting circuits, and enabling many electronic functions. Size of the band gap in a semiconductor determines the color of light it can absorb or emit. Materials with larger band gaps emit higher energy, shorter wavelength light like blue or ultraviolet. Smaller band gaps emit lower energy, longer wavelength light like red or infrared. This principle is used in everything from LED displays to solar panels, where precise control of light is essential. Organic semiconductors are made from carbon-based molecules and have unique band gap properties. Their flexibility and tunable band gaps make them ideal for applications like flexible displays, organic solar cells, and wearable electronics. By designing specific molecules, scientists can create organic semiconductors with custom band gaps for a wide range of uses. Two-dimensional materials like graphene and transition metal dichalcogens have attracted attention for their unique band gap properties. While graphene has no band gap, materials like molybdenum disulfide have a direct band gap, making them promising for next-generation transistors and optoelectronic devices. Research into 2D materials is opening up new frontiers in electronics and photonics. Insulators have a very large band gap, making it nearly impossible for electrons to move from the valence to the conduction band under normal conditions. This property makes insulators perfect for preventing unwanted current flow in electronic circuits. Materials like glass and rubber are classic examples of insulators, and their wide band gaps are key to their function. Photodetectors are devices that sense light and convert it into electrical signals. The band gap of the semiconductor material determines which wavelengths of light the detector can sense. By choosing materials with the right band gap, engineers can design photodetectors for everything from visible light to infrared and ultraviolet detection, enabling applications in cameras, sensors, and scientific instruments. Solar spectrum contains light of many different energies. To maximize solar cell efficiency, the band gap of the semiconductor should match the energy of the most abundant photons in sunlight. Too large a band gap and much of the sunlight passes through unused. Too small and the energy is wasted as heat. Finding the optimal band gap is a major focus in solar cell research. Thermoelectric materials convert heat into electricity, and their performance depends on the band gap. A suitable band gap allows for efficient separation of charge carriers, maximizing the conversion of thermal energy to electrical energy. Advances in band gap engineering are helping to create better thermoelectric devices for power generation and cooling applications. Many sensors rely on the band gap of semiconductors to detect changes in light, temperature, or chemicals. By selecting materials with the right band gap, engineers can design sensors that are highly sensitive to specific stimuli. This principle is used in everything from smoke detectors to medical diagnostic devices, making band gap knowledge vital for sensor technology. Semiconductor lasers or laser diodes use materials with a direct band gap to generate coherent light. When electrons recombine with holes, they emit photons of a specific energy determined by the band gap. By engineering the band gap, lasers can be made to emit light at different wavelengths, enabling applications in communications, medicine, and industry. Transparent conductors are materials that conduct electricity while letting light pass through. They have a wide band gap that allows visible light to pass but still have enough free electrons for conductivity. These materials are used in touchscreens, solar cells, and display panels, combining transparency with electrical performance. Power electronics require materials that can handle high voltages and currents. Wide band gap semiconductors like silicon carbide and gallium nitride are ideal for these applications. Their large band gaps allow devices to operate at higher temperatures and voltages, making them perfect for electric vehicles, power grids, and renewable energy systems. Memory devices like flash drives and RAM use semiconductors with carefully engineered band gaps to store and retrieve data. The band gap controls how easily electrons can move and be trapped, enabling reliable data storage. Advances in band gap engineering are leading to faster, more efficient, and higher capacity memory technologies. Quantum computing is an emerging field that uses quantum bits or qubits to perform calculations. Some types of qubits are made from semiconductor materials, where the band gap plays a role in isolating and controlling quantum states. Precise band gap engineering is essential for building stable, reliable quantum computers that can outperform classical machines. Flexible electronics use materials with tunable band gaps to create bendable, stretchable devices. Organic semiconductors and 2D materials are leading the way in this field, enabling new products like foldable phones, wearable sensors, and flexible displays. The ability to engineer the band gap for flexibility and performance is driving innovation in consumer electronics. Environmental sensors monitor air quality, water purity, and other factors using semiconductors with specific band gaps. These sensors can detect pollutants, toxins, and other substances by measuring changes in conductivity or light absorption. Band gap engineering allows for the creation of highly sensitive, selective sensors for environmental monitoring and protection. Medical devices like imaging sensors, diagnostic chips, and wearable monitors use semiconductors with tailored band gaps. These materials enable precise detection of biological signals, light, or chemicals, improving the accuracy and reliability of medical diagnostics. Band gap engineering is helping to advance healthcare technology and patient care. Communication devices like smartphones, Wi-Fi routers, and fiber optic systems rely on semiconductors with specific band gaps for signal processing and transmission. Materials with the right band gap enable high-speed data transfer, efficient signal amplification, and reliable connectivity, forming the backbone of modern communication networks. Modern lighting technology, from energy-efficient bulbs to smart lighting systems, uses semiconductors with engineered band gaps. By selecting materials with the right band gap, manufacturers can produce lights with specific colors, brightness, and efficiency. This has revolutionized the way we light our homes, offices, and cities. Display technologies like LCDs, OLEDs, and quantum dot displays all rely on semiconductors with carefully chosen band gaps. The band gap determines the color, brightness, and efficiency of each pixel, enabling vibrant, high-resolution screens for TVs, monitors, and smartphones. Advances in band gap engineering are leading to even better displays. Automotive electronics, from sensors to power systems, use semiconductors with wide band gaps for reliability and performance. These materials can withstand high temperatures and voltages, making them ideal for electric vehicles, advanced driver assistance systems, and automotive safety features. The band gap is key to the future of smart, efficient transportation. Security devices like biometric scanners, surveillance cameras, and secure communication systems use semiconductors with specific band gaps. These materials enable accurate detection, fast processing, and secure data transmission, helping to keep people and information safe in an increasingly digital world. Artificial intelligence systems rely on powerful processors made from semiconductors with optimized band gaps. These materials enable fast, energy-efficient computation, supporting machine learning, data analysis, and intelligent automation. Band gap engineering is helping to push the boundaries of what AI can achieve. As technology advances, new applications for semiconductors and their band gaps are emerging. From flexible electronics to quantum devices, the ability to engineer and control the band gap is opening up exciting possibilities. Researchers are exploring novel materials and structures to create the next generation of electronic and photonic devices. Despite its potential, band gap engineering comes with challenges. Creating materials with precise band gaps requires advanced techniques and careful control of composition and structure. Researchers must also balance performance, cost, and scalability to bring new technologies to market. Overcoming these challenges is key to unlocking the full potential of semiconductors. Future of band gap research is bright. Scientists are exploring new materials such as perovskites and topological insulators with unique band gap properties. Advances in nanotechnology and material science are enabling unprecedented control over electronic and optical properties. As our understanding deepens, band gap engineering will continue to drive innovation in electronics, energy, and beyond. Wrap up: the band gap is a fundamental concept in semiconductor physics, shaping the behavior and applications of countless electronic devices. From computers and smartphones to solar cells and sensors, understanding and engineering the band gap is at the heart of modern technology. As research continues, the possibilities for new materials and devices are virtually limitless. Thanks for joining us on this journey into the world of semiconductors and the band gap.